From Classical to Physical Realizable Hamiltonian Mechanics by Francis T.S. Yu. Since our universe is not a zero-sum energy subspace, the total energy of a hypothetical machine, for example, Hamiltonian Mechanics, must be conserved. That is the first law of thermodynamics, for which firstly I will show that classical Hamiltonian mechanics is not an energy-conserved machine. Then I will formulate a new energy-conserved Hamiltonian machine, which is physically realizable. Since Schrödinger's quantum mechanics is a legacy of Hamiltonian, but designed for particles that travel at the speed of light, this quantum machine is a fantasy timeless machine. I shall reformulate it to become a temporal t greater than 0 quantum machine, which will survive within our time-space. Since Schrödinger's mechanics misled us for decades, it is about time for us to get back to a physically realizable issue. Otherwise, we'll forever be trapped within a fantasy, timeless land of quantum world. Yet if there was a creation hypothesis, there must be a de-creation hypothesis. Why mathematics is not science. Every fundamental equation represents an interpretation, but an equation is not science. For example, a rest particle of mass m is situated within an empty space as depicted in Figure 1. Its total energy due to gravitational pull is its potential energy, Pe, defined as Pe equals m times g times h, where m is the mass, g is a gravitational constant, and h is the height, which is a timeless equation. Since this scenario is hypothesized within a timeless platform, Hamiltonian classical mechanics is a timeless machine. But if the same machine is situated in our time-space as depicted in Figure 2, then the particle's potential energy must be the total Hamiltonian energy, in which we see that as soon as the particle falls on the ground, its potential energy is totally converted into its kinetic energy, Ke, as given by K equals 1/2 mv squared, where v is the particle's velocity, for which two possible equations can describe the particle's energy transition from potential to kinetic energy, as given by Pe minus Ke equals 0, or Pe equals Ke. But one is a zero sum and the other is a non-zero sum equation. For instance, the zero-sum energy equation suggests that negative energy can exist, while Pe equals Ke implies that a particle's potential energy decreases as there is an equivalent amount of particles' kinetic energy increase, or vice versa. From which we see that it's not how rigorous mathematics is, but it is the platform that guarantees the physical realizability of its solution. Non-realizable classical Hamiltonian mechanics. Let me refer to a classical Hamiltonian mechanics shown in Figure 3 for which the Hamiltonian operator takes place, that is, the operator H equals the potential energy plus small p, where small p equals mv, the particle's momentum, v is the particle's velocity, and a is its acceleration, from which the particle's momentum is independent from its potential energy. Aside, it is not a physically realizable paradigm. Its potential energy has nothing to do with its momentum. Furthermore, if an eigenstate wave function psi is incorporated, the Hamiltonian wave equation takes the form h phi equals the sum of p e plus small p times phi equals 0. But it is not an energy conserved equation, for which psi is not temporal, that is, t greater than 0. Let me further note that justification of introducing an eigenstate of phi is assuming its platform subspace is non-empty. Like electromagnetic wave propagation, that is Maxwell's equation, was formulated within a non-empty space platform, yet timeless. But it's the time of the platform that moves the wave, but not the wave that changes the time of the platform. In other words, without the existence of time of the platform, psi cannot propagate with time. Aside, the classical Hamiltonian is not a physically realizable operator, but it has a critical issue for the inclusion of particles' momentum, that is, F equals ma, since it has nothing to do with the particle's potential energy. Nevertheless, it was the empty space paradigm that made classical Hamiltonian mechanics a timeless fantasy machine. A review of classical Hamiltonian mechanics. In view of Hamiltonian classical mechanics, where the Hamiltonian operator represents a one-dimensional x operator given by h equals minus 1 over 2m times h squared del squared plus the potential energy. Firstly, it is not an energy conservation operator where del squared equals the derivatives with respect to xi and x sub j is a Laplacian operator. Secondly, introducing an eigenstate function psi based on a particle wave dynamics idea, of which Hamiltonian wave equation takes the form v minus 1 over 2m times h squared del squared multiplied by psi equals e psi, where v is the particle's potential energy and E is the kinetic energy associated with momentum P equals mv, and V is the particle velocity. Nevertheless, wave function of phi did not tell us whether it's electromagnetic or gravitational wave in nature. Furthermore, from a reality standpoint, Hamiltonian had hypothesized a scenario within a non-empty yet without space-time. In other words, the introduction of psi is strictly from particle wave dynamics idea, but Hamiltonian mechanics was developed within an empty space paradigm. Nonetheless, by rearranging the preceding equation, we have the following well-known Schrödinger's zero-summed wave equation as given by del squared psi plus the quantity 1 over 2m divided by h squared times the quantity Ke, the kinetic energy minus the potential energy, times the phi function equals 0, which is not energy conserved, which is why the solution of psi is independent of time. A note on Hamiltonian's legacy. Since Schrödinger's machines is the legacy of Hamiltonian classical mechanics, it is fair to say that if classical Hamiltonian mechanics fails to exist within our space-time, then it is difficult to legitimize that Schrödinger's quantum machine is physically real. Nevertheless, the major application of Schrödinger's mechanics is restricted to a very small particle that travels at the speed of light, where Bohr's quantum leap was adapted. But Bohr's atomic model was also hypothesized within an empty space platform, of which his quantum leap is not time and band limited. See reference 2. In view of the current limit of our physics, it does not permit objects to travel at or beyond the speed of light, for which I will discuss an application as limited by a packet of wavelet, i.e. the quantum leap. As for the implementation of Hamiltonian to larger objects, such as to planetary systems of cosmological scale, or others, remain to be seen. Reference 2. Book by Francis Yu, The Nature of Temporal T greater than 0 Science, a Physically Realizable Principle. An energy-conserved Hamiltonian. Since our universe is an energy conservation dynamic subspace, every hypothesized mechanics within our space-time must obey the law of energy conservation. When the Hamiltonian machine is submerged in our time-space as depicted in Figure 4, the Hamiltonian operator takes the form h of t is defined as the potential energy as a function of time equals the kinetic energy as a function of time for t greater than 0, which is a non-zero-summed energy conservation operator which changes with time. From this we see that when a particle's potential energy decreases, there's an equivalent amount of the particle's kinetic increase, as given by h of t is defined as minus derivative of the potential energy as a function of time with respect to time equals the derivative of the kinetic energy as a function of time with respect to time for t greater than 0. It shows that total energy of the Hamiltonian operator is conserved, which is equal to the particle's original potential energy at the initial state, that is t equals 0, that is the potential energy at t equals 0 equals m times g times h, where h is at time t equals 0. From which we see that without the existence of time of the subspace that the Hamiltonian is embedded in, there would be no transferring of potential to kinetic energy with time. This is the reason that a physically realizable Hamiltonian must be an energy-conserved operator which changes with time. A footnote. Nevertheless, mathematically oriented Hamiltonian scientists had done one thing right for introducing an eigenstate wave function psi in the analysis. Although Hamiltonian was developed within an empty space model, but the implementation of psi was surprisingly clever, though it must be due to particle wave dynamics standpoint, although the Hamiltonian was developed on a no space platform. Yet particle wave dynamics indicates that it has empty space medium but timeless. Like many of the classical sciences, emptiness is supposed to have no substance in it and no time. But psi is a wave dynamics that needs non-empty space to support. The same like Maxwell equations were developed on an empty space platform, but it shows that electromagnetic wave propagates within a dielectric medium, but without any constraint within our time-space. This must be the reason theoretical physicists analyze how light propagates from point A to point B, but a fundamental physicist needs to know a section of time delta t with an amount of energy delta E to move a wavelet from point A to point B. Since within the regime of quantum mechanics, things travel at the speed of light, but it is a section of time with that amount of energy, that is, delta energy is a function of delta time, that makes it happen, which cannot be simply ignored. Yet we have ignored this price, that is, delta E is a function of delta t. If not for decades, it must be for over a century. Einstein's space-time continuum could have been avoided. One of the geometrical coordinate systems that does not have a non-zero-sum feature is spherically coordinate geometry as depicted in Figure 5. Figure 5 shows a spherical geometric space-time continuum, for which if Einstein's space-time continuum was developed from a spherical coordinate system, he might not have a zero-sum space-time continuum, of which Dirac's parity physics would not have developed, as can be seen in Figure 6, since every past realizable space-time universe exists only once. Figure 6 shows one and only one physically reality which cannot be repeated even if it travels at the speed of light. Although spherical geometry space-time is non-zero-sum space-time, yet it is still an empty space issue against its existence within our temporal universe, that is t greater than 0, from which we see that is not how rigorously mathematics is, but it is the physically realizable platform that guarantees a legitimate solution. Nevertheless, the foundation of our modern physics was built on Einstein's four-dimensional space-time continuum. No wonder our modern science is so wrong. Temporal Hamiltonian and energy conserved operator. In view of the energy conserved Hamiltonian operator as given by H as defined as potential equals kinetic energy, which is a timeless equation unless the Hamiltonian operator changes with time. That is, it's temporal for time greater than 0, from which it tells us H machine works only if it is submerged within our space-time. In other words, anything exists within our universe coexists with time. For example, when time moves on from the present moment, there is an amount of the particle's kinetic energy increase, which is equivalently equal to an amount of the particle's potential energy decrease, as given by an equation shown in the slide, in which we see that P, the potential energy, decreases as the height decreases as the function of time, but at the same time the particle kinetic energy increases rapidly since the particle's velocity increases. In view of the Hamiltonian operator as a non-zero-sum operator, it is a physically realizable machine that obeys all the laws of nature, that is, law of time, law of energy conservation, and others. A radii Hamiltonian operator. Since Hamiltonian mechanics is a radial machine, that is, radii dimension, where the height can be replaced by a distance and a particle velocity is an inward radii v of r at a time, as depicted in figure 7, of which a radii Hamiltonian takes the form shown in the slide. Since the particle's potential energy is a convergent energy vector as given by the second equation, where minus del dot is a radii convergent operator and S is an inward radii energy vector, from which the potential energy represents a gravitational convergent energy vector. Strictly speaking, the application of Hamiltonian to modern physics is a complicated issue. For example, as applied to large-scale planetary systems or to small particles traveling at the speed of light. Strictly speaking, every temporal mass has a life, that is, mass is the function of time. The constraints on m of t degrades with time. Nevertheless, an extreme case due to mass annihilation is given by equation 3, which shows that a particle's kinetic energy diverges at the speed of light as depicted in figure 8, where del dot is a divergent radii operator and S is a radii energy vector. From this, a mass extinction divergent energy kinetic energy vector can be used to simulate the creation of our dynamic universe, as will be seen in the following slides. Figure 7 shows a spherical coordinate diagram of the particle's convergent potential energy within our space-time. Figure 8 shows a spherical coordinate diagram of the particle's kinetic energy divergent explosion within our time-space. Origin of our universes. Nonetheless, the upper limit of a particle's kinetic energy is reached as its velocity reaches the speed of light, for which the mass must be annihilated into electromagnetic radiation, which is equal to the total energy of mass, that is, energy is 1/2 mc squared, as given by equation This is essentially the same equation for the creation of our temporal universe, that is t greater than 0, from which, as our universe is expanding at the speed of light, it creates a divergent distribution of all substances, that is, all degraded energy and others, from the center of the Big Bang explosion. For this, it creates a convergent potential energy due to gravitational force with the expanding universe, as shown in Figure 9, in which we see that more and more degraded substances are produced, that is, dark matters and others, as the entropy of our universe increases. Yet this creation process will not stop until our universe exhausted all its kinetic energy that was created our universe. And this at the point of infinity, that is t approaching infinity, where our universe uses up all its useful energy provided by its kinetic energy. But before it reaches the end of its divergent creation, there will be a sufficient convergent potential energy taking place to reverse the creation process as from all the degraded matters. Figure 9 shows a divergent creating process primarily due to mass annihilation, where its boundary is expanding at the speed of light. Decreation of our universes. Nevertheless, before it reaches the end of creating our universe, that is, exhausting all its useful energy, it will eventually build up a strong convergent gravitational potential energy from all the degraded matters, that is, dark matters and others, to overcome the divergent creating process, in which we see that the decreating process might have started soon after the Big Bang exploded, as depicted in Figure 10, from which the dynamic activity within our universe will be subsiding. For example, entropy increases or slowing down at the end of our universe's life. This means that the remaining useful kinetic energy within our universe is at its lowest end. At this point, its convergent gravitational potential energy will overtake its divergent kinetic energy due to an inward gravitational field created by all the degraded matters. Since there are two major energies responsible for creation and decreation of our universe, divergent kinetic energy is the one contributing to creation, but convergent potential energy must be the one contributing to decreation. Since convergent potential energy has started to build up after the Big Bang, yet it is the convergent gravitational field that is balancing the dynamic expansion of our expanding universe. Otherwise, it will be a flyaway, chaotic universe. Figure 10 shows a convergent decreation process due to gravitational force from a convergent potential energy developed by the degraded matters. From creation to decreation of our universes. Since creation of our universe can be understood from the Hamiltonian standpoint, which was started from its divergent kinetic energy explosion, from which I had shown that the decreation of our universe must be from its convergent potential energy built up by gravitational force from its degraded substances, that is, dark matters and debris. Since only two dominant forces within our universe, space, where kinetic energy explosion was derived from mass annihilation, but the total potential energy was due to Newtonian gravitation, of which it is fair to accept that the decreating universe is due to convergent gravitational potential energy, which creates the Big Bang scenario, but it is within a pre-existent temporal space scenario to initialize the possible explosion. This is to rebut the conventional wisdom that our universe was created from a zero-summed empty space paradigm, which is depicted in Figure 11. The figure shows a convergent, decreating universe after a divergent creation from the Hamiltonian standpoint. This paradigm may be one of the closest to the truth, since science is approximated. Figure 11 shows a convergent decreation due to gravitational force after the end of a divergent creation of our universe. A realizable Hamiltonian quantum machine. Since energy from mass annihilation is huge, this may be the reason why Schrödinger had opted to use Bohr's quantum leap into his machine. Nevertheless, like all classical mechanics, Bohr's atomic model was hypothesized within the same empty space platform, for which his atomic model is not a physical realizable model. Instead, a realizable Bohr's model is hypothesized in Figure 12, in which a quantum leap is a time and band-limited wavelet, that is, the change in energy is equal to h times the change in wavelength, where h is the Planck's constant, from which Hamiltonian quantum operator takes place, shown in Figure 1, which is known as Hamiltonian quantum wave equation as given by equation 2. Since the time-dependent Hamiltonian is constrained by t greater than 0, the solution in psi of t is temporal, unlike Schrödinger's psi of t, which is time-independent. Figure 12 shows a realizable Bohr's atomic model situated within our time-space. A temporal Hamiltonian wave equation. When we incorporate a temporal eigenstate wave function psi with a Hamiltonian operator, a Hamiltonian wave equation takes the form shown in the first equation. In partial differential form, we have the second equation, where we see that as a particle m falls, it loses its potential energy, but it is a gain of its equivalent amount of kinetic energy. Notice that if a physically realizable Hamiltonian wave equation in which the overall amount of energy is conserved. However, there are two cases to be discussed. First is the Hamiltonian wave equation application to very large objects, and the other is to small particles traveling at the speed of light. Nevertheless, regardless how small a particle is, it cannot travel at the speed of light, which is the current constraint of our physics. In other words, when a particle reaches the speed of light, it must be self-annihilated into a package of electromagnetic wavelet radiations, from which the idea of particle wave dynamic is equivalent to, but not equals to, a wave as a particle in motion, or a particle in motion is wave. For example, Bohr's quantum jump radiation is equivalent to a particle wave dynamic, but not due to the particle's annihilation. Thus, as a falling object's velocity reaches the speed of light, the object's potential energy is assumed to be converted to its kinetic energy. Kinetic energy is 1/2 mc squared, c being the speed of light. But for a falling object's velocity below the speed of light, its kinetic energy is 1/2 mv squared. Back to the origin of our universe. Without time within a space, even light cannot propagate, for which we have to agree that the origin of our universe had to be started, that is, the excitation at time equals 0, within a space of time, that is, causality t greater than 0, which is a greater temporal space that our universe is embedded in, reference 3. As from the Hamiltonian standpoint, it is an isolated mass of m that must be situated within a temporal space as shown in figure 13. Since without the existence of time within a space, it is impossible for mass to convert to energy. If this is still not a physical logic for you to accept, then I must have run out of all the possible scenarios. Certainly mathematics is not an option, since it is not physics. A fundamental physicist treats mathematics as physics. That is wrong. This is precisely why theoretical physics had been hijacked by mathematical-oriented physicists. In view, the hypothetical scenario has no potential energy. The only option is to convert its mass into energy by means of mass annihilation. Fortunately, the hypothetical particle is embedded within a space having time, but mass annihilation needs an energy to trigger. A fair answer is that m has to be a gigantic mass created by a huge amount of degraded substances, which were collected by their gravitational forces that created a gigantic convergent gravitational potential energy to trigger the explosion, from which, without the convergent potential energy, it has no way to initiate the explosion. And this is the origin of our universe, reference 3. Although science is approximated, yet Einstein's four-dimensional space-time continuum is so wrong. Figure 3 shows a Hamiltonian particle embedded within a temporal, that is t greater than 0 space. Conclusion. The essence of this presentation must be a physical realizable for all fundamental principles, that is, machines, since laws and theories cannot be virtual, as is mathematics. In view of our current modern physics, it was hijacked by mathematical-oriented theoretical physicists. If not for decades, it must be for centuries. Since principles and laws were rooted by fundamental analysis, yet mathematics is not science. It is becoming more harmful than beneficial by scores of theoretical physicists to keep promoting those fundamental principles which are actually existed within our universe, for which the classical Hamiltonian is one of them that I have presented. My final question is this: would you want your students, children, and grandchildren to be continually learning all those fantasy, non-existent principles in sciences? For example, a couple of years before the COVID pandemic, I was invited to a particle and astrophysics conference in Amsterdam. After I presented my talk, a young theoretical physicist approached me with sincere advice. "Professor, why don't you learn our physics?" I replied, "That Professor Yu is 87-year-old. Are you encouraging me to spend another 20 years to learn your kind of physics? Yet I have a question to myself, since I have discovered our modern physics is so wrong. Why should I spend 20 years to learn it before getting started?" Thank you. Final remarks. Let me differentiate a distinctive difference between a theoretical physicist and a fundamental physicist. A theoretical physicist is researching how an object travels at the speed of light from point A to point B. But a fundamental physicist is researching for principles that show a section of time delta t with an associated amount of energy delta E that is needed for a wavelet traveling at the speed of light from point A to point B. And this is precisely why theoretical physicists are so weird and fundamental physicists are very realistic.